Welcome to another video. So in this video, we finally get down to putting some things together and starting to solve some logarithms and then exponential equations in the next couple videos. So when we're solving logarithms, I want to say that this would be a special case, much like we saw a special case with exponentials. We're going to deal in this video with the special case of what would happen if you have an equation where every single term happens to be a logarithm and a logarithm with the same base. Can we solve it very, very simply? And the answer is yes. If we have an equation with all of our terms being logarithms and they all have the same base and we can combine them all and get one logarithm on one side equal to another logarithm on the other side with the same base, then we can set the insides of those arguments equal to one another, much like we do with exponentials. That's what we're going to learn in this video. I do want to say that this is not the general case. So in the next video, we're going to say, well, what happens if you can't do that? Well, then we're going to need exponentials. And in general, if you ever want to solve a logarithmic equation, you are going to need an exponential to solve that. The only exception to that is if you can have this situation where you have common bases. So let's jump right into it. What would happen if you have one logarithm equal to another logarithm with the same base? Well, if that's true, the only possible way these things could be equal is if their insides, x and y, or the arguments of these, are also equal. We saw something very, very similar in solving exponentials with common bases. We said, hey, if our bases are equal, then our exponents also have to be equal to keep this equation true. And that's the same situation we have. So the notes I have down here for you are the same thing as the notes that I just mentioned. This only works if every term's a logarithm. And only if you have the same bases, because then, and only then, can you set the insides equal. If these were different bases, you'd be done. There's not really much we can do as far as a special case is concerned with that. Now, we can do some things with exponentials, but not if our bases are different and not if we have a constant. So how do you tell this video from the next one? If you have a constant up here being added or subtracted, not all logarithms, or different bases, then this does not work. This is a very, very special case and just gets our feet wet with how we start thinking about solving these and that we can do it with added exponential in some cases. Also, I want to tell you, just a reminder that when we start any sort of a logarithmic equation, before we start combining things, we really should be thinking of the domain and understanding that in logarithms, the inside of your logarithm always has to be strictly greater than 0. It can't even equal 0. So we're going to do a lot of things up here like combine some logarithms. Oh yeah, we need to know how to do that. Combine some logarithms with division. And we'll be thinking, well, aren't we breaking a domain rule by doing that? No, because all of the insides of our logarithms inherently have to be positive to make them work anyway. Positive means you can't even let them equal 0. So anything that does is not okay. Anything that creates an inside negative is not okay. What that means, if you want to wrap everything in a nutshell, is whatever our solutions are, we need to check those to make sure that our insides of our logarithms are not becoming negative by plugging them in. What that doesn't mean. You don't just go crossing out every negative. I know it's kind of fun, but that's not the idea. The idea is check your solutions, make sure they are making the inside of your logarithms positive. So let's get into it. Log base 4 of x plus 2 equals log base 4 of 8. This is a very simple concept. This is a very special case. We notice that there's logarithms everywhere. There's one on one side, one on the other side, and they have the same base. When this happens, you can set your insides equal. That's plain and simply what all of this says. And by doing that, we get something that's very nice to solve. Subtracting 2, we get x equals 6. Take the time, check your work. Does this make that negative? No, it looks good. And log base 4 of 8, 6 plus 2 is 8, equals log base 4 of 8. And that's a true statement. So that is our one and only one solution. What we do from here is when we take a look at our equations and we see that we have logarithms, I want you to start categorizing them. Do I have all logs with the same base, or do I have logs with different bases, or some terms that aren't logarithms, like constants or other variables? Well, that would be a different category. So we're going to take a look at it. Do I have in this equation all logarithms of the same base, no other terms added or subtracted? Oh, yeah, that looks good. Oh, okay, I'm going to put this in my special category of I'm going to have logarithms with the same base. I'm going to be able to set my insides equal to one another. However, in order to do that, it really does have to look like that. This is where all of our combining of logarithms comes in. Combining of logarithms means that if you have more than one of them with the same base and they're added or subtracted, you can combine them to one logarithm. If you have any coefficients in front, including that negative, you can move those as exponents. And so we do that first. We make it so that we literally have one logarithm equal to another one, nothing added, subtracted, multiplied, divided. So that 3 being a coefficient means that I can move that as an exponent. And get log base 2 of x to the third power. On the right-hand side, because that negative really stands for a -1, you can move that as an exponent and get log base 2 of 27 to the -1 power. This is what we're looking for. We say, hey, look at this. We got 2 logs, the one on each side, there's nothing added, subtracted, multiplied, divided, and they have the same base. If these are going to be equal, it can only be the case that our insides, our arguments are also equal. So there's not really much work to show here. We don't have to cross anything out. We just need to understand that the only way this actually happens, much like a common basis in exponentials, is if x cubed equals 27 to the -1 power. Now, are there ways to do this with exponentials? And the answer is yes. If we were really smart about it, we could say, you know, I can do anything I want to an equation pretty much, as long as I do it to both sides. Could you treat both of these as an exponent of some other base? Yes, we can. Now, if you pick that base of 2, why a base of 2? Why would I do that? Well, the logarithm has a base of 2. If I choose this as an exponent of some exponential with a base of 2, I've inherently matched a function to its inverse. I've composed them. I have a base matching a base, that would cancel. Base matching base, that would cancel. It would set x cubed equal to 27 to the -1 power anyway. That's exactly what we're doing. We're just making it a little bit quicker. So now comes the work. Usually this is where I stop really teaching, and this is stuff that we've seen before. So this is going to be some more basic algebra. Things like, you know, just remember that a -1 power means a fraction, like 1 over 27. Remember that when we have an x to the third power and it's isolated or x to any power, we can match the power to the root and take a radical of both sides. Things like a cube root. Also understanding that if we're doing this with a square root, we'd have a plus and minus, and we're probably going to have to watch some of our solutions on that, because we cannot let any of these solutions make any of our arguments where we started from negative. We don't check our work down here. We check our work up there in the original. So taking a cube root, we get x equals 1/3. We're going to pause for just a second, make sure we check this. Take this, plug it into the arguments of your logarithm. Just evaluate that. Make sure that they are not 0 and not negative. So 1/3 in here does not cause it to be negative. Notice what I'm not doing. I'm not checking it here. Why not? If that were a 2 and that were a power 2, and this happened to be a negative, it would make that look like it's positive. But that's not where I'm checking it. I'm checking it here, where it originally came from. So just be careful on that. Check it in your original equations. All right, let's move on just a little bit. We got 3 more. This one's going to be pretty quick. The other ones are also fairly quick, but we want to make sure that we're seeing these appropriately. So here's the way to categorize it. We're taking a look at it saying, I have logarithms, of course. Am I going to need an exponential? Am I going to just use common bases? If all of your terms, and there's 4 of them here, are logarithms with the same base, we can combine them. And we are looking to get one logarithm equal to another one with the same base. Now, are there other ways to do this? There are, and they would involve some exponentials, but we gather all of our logarithms on one side, combine them, and a constant on the other side, even if it's 0. However, that combining is a lot more work than we really need if we have terms that are all logarithms. Just combine your sides individually. Combine the left side, combine the right side, and then set the insides equal. Most of the time, that's easier. So let's go ahead and do that. I'm taking a look at it and thinking, it only works if I have 1 log equal to 1 log. So I'm going to combine my left-hand side, remembering all those properties we learned. If we have 2 logs that are being subtracted, it's going to create 1 logarithm with a quotient in it. And the order is really important. All the logarithms that were positive or added created factors on the numerator. all the logarithms that were negative or subtracted created factors on the denominator. We get the same thing over here. Now, we had a base of A. Base of A, I don't even know what that is. It doesn't matter, because it didn't really matter. That was a base of 2. Why not? Because what we did with it, with our exponential, is we put 2, we put 2. We just matched the base. Well, if we have a base of A and base of A, what would we do? Whatever that base is, provided it's valid, is we would put a base of A and a base of A. It doesn't matter what that base is. What matters is that you have the same base. That's the key here. 2 logarithms, they're equal to one another with the same base. Much like 2 exponentials equal to one another with the same base. We set the exponents, or the insides, equal to one another. Here we have the same base, that the insides of logarithms equal to one another. So we have log base A equals log base A. This is only true if our insides are equal. And this is what I was saying a little bit earlier. Right now, all that's going to happen is that we have some kind of old algebra. Remember, we can do things like proportions. If you have one fraction equal to another fraction, you can certainly find a cross product. So we're going to multiply these. And I hope you remember, if you get a power 2 or higher, your idea in general is, unless you can isolate that power 2 or higher, you're going to get everything on one side. You're going to factor it, or use one of the techniques that I've taught you in this class and solve it. You're going to get 0 on one side, because you're essentially going to use a 0 product property over and over again. If you don't have that, like we had that here. We're able to isolate the power and take a cube root. We're going to have a power 2 and a power 2. We're going to have to see what happens with this. Now, if we can cancel out the power 2, great. But in general, we get everything on one side. If not, if you can cancel the power 2, or if you just have a power 1, don't try to factor it. Try to solve it directly. We're going to see that right here. So x squared plus and minus, plus 3x and minus x is plus 2x minus 3. We get this x squared plus 4x minus 12. Now, right here, what I was just saying is we have a power 2. In our head, we're probably thinking we're going to factor this thing. And that would be true if we didn't have a power 2 that was going to cancel out. So we're going to simplify, or we're going to subtract x squared on the idea of let's get everything on one side. As soon as we get rid of it, though, that's no longer a factoring problem. That's a linear. And that means just subtract your smaller variable, get rid of your constant, and then divide. Adding 12. So we work that out. We get, if we add 12, we get 9 equals 2x. Divided by 2, we get 9 halves. Is it okay to get a fraction? Sure. Is it okay to get a negative? Sure, as long as it doesn't make any of my original arguments negative. So we would plug this in, and you're going to check. Don't check it here. Check it here. So 9 halves minus 1. Well, 9 halves is, what, 4.5? So that would be like 4.5 minus 1. Well, that's positive. 9 halves plus 6, that's positive. Minus 2, that's positive. Plus 3, that's positive. None of them are 0. None of them are negative. This is a valid solution for us. And you can work it out and make sure that it actually does work, but that's going to be just fine. Really what we're looking for is make sure that does not cause any of your inside your logarithms to become negative or 0. Now, I mentioned something a while ago I really want to delve into a little bit more. Why are we able to divide this by this in one logarithm? And I don't mean the property. The property says we can do that, and we can do that. Why are we able to from a domain standpoint? Because at this point, you should be thinking, well, wait a minute. I would have a big problem if x equals negative 6. Well, that's true, because now you have this denominator that if you plugged in -6, you would have something over 0, something that's undefined. That is true, that's a problem. But look, isn't that the same problem that we have here anyway? Like if x plus 6 equaled 0, if you plugged in -6, you would get a logarithm with 0 on the inside. Logarithms have a vertical asymptote there. You can't even plug in 0. You can't even have 0. So we have the same problem anyway. In fact, it's more restrictive than that. We don't just disallow 0. This thing can't even be negative. So this is strictly greater than 0 anyway. Strictly greater than 0, not equal to 0. So because the natural domain of a logarithm is already not allowing 0, it's okay to do things like make division and not worry about the domain because you're not creating anything additional. You already knew that couldn't equal 0. It can't even be a negative. When we put it like this and have that on a denominator, it's not creating another, you can't equal 0. It already can't do that. So we're not breaking any rules by doing it. I just want you to see that we're not cheating the system. It's already there. We're just using it and not having to define it further. Hope that makes sense to you. I hope this whole thing makes sense to you. I hope you're seeing that, yeah, if I have two logarithms equal with the same base, I can just set the insides equal much like we can exponentials. We're just combining on each side, setting the insides equal. We're using all the stuff about combinations, and if we don't have all logarithms, this will not work. We're going to come back with 2 more examples and move on to a different video. Let's move on a little bit. So in our next example, I'm going to start really kind of modeling my thinking about how exactly we differentiate between this and a general logarithmic equation. So when we look at it, you're just looking really for one thing. Are all of my terms logarithms with the same base? If so, combine both sides, set the insides equal. If not, we're going to have to use an exponential. We combine both sides as much as, actually, we get all the logarithms on one side, combine as much as we can, and have a constant on the other side. So here we're looking at this saying every single one of those terms is a logarithm with the same base. Looks really good. Let's combine all the logarithms that we have on each side. Could you get everything to one side and combine it? Yes, you could. And you would have a 0 on the other side. Could you use an exponential? Yes, and base to the 0 power would give you 1 equal to the inside. You can do that. I might show that to you on one of these examples, just to let you know as a preface for the next video. But you don't have to do that. So if we have this, all we're really looking to do is one logarithm equal to another. We have to move our coefficients as exponents first, and then combine the logarithms into 1. So we see a coefficient of 2. That's going to become an exponent on that 5. And the same thing is going to happen with this too. Also, I hope that you remember that we don't have to move that negative, just the 2. Now you can move the negative and deal with a fraction like this 1 over 10 squared if you really want to, but it's a little bit easier to use that minus as a way to create division inside of one logarithm as a fraction, rather than use that negative to create a fraction in one logarithm, then multiply and get the same fraction anyway. That's a little bit more cumbersome to do mathematically. So we typically leave the sign, unless it's the only sign we saw in the second example. If that's the only sign in front and it becomes a negative, that's okay, but typically we'll leave that as a minus rather than choosing it to represent a negative. Now, because we have more than one logarithm on each side, we're going to have to combine this via addition or subtraction, creating multiplication and division within one logarithm, respectively. So we look at it and go, okay, log base 3, log base 3. A minus sign between two logarithms creates a division or a quotient within one. Same base though. Added or positive creates numerator factors. Minus or negative creates denominator factors. Added or positive creates numerator factors. Minus or negative creates denominator factors. I've also squared the 5 and squared the 10. Now we're ready. When we see these logarithms equal same base, we know that the only way this happens is if the arguments of logarithms are also equal. So we set them equal. We get another proportion, and we're still going to cross multiply. We're not seeing any power 2's, no exponent higher than 1, which means this is a linear, and that means that we're not going to be factoring. We're just going to be subtracting the smaller variable, removing any constants around that variable if we have to. We don't have here. We don't have anything added or subtracted to that variable term. And then dividing. And we get 1/3. We're going to check that. So 1/3 into here. 1/3 into that argument does not make that negative or 0. That's a good thing. That's constant. That's okay. 1/3 plus 1 is 1 1/3. That's not 0 or negative. We're okay here. And that's 10. That's going to be a valid solution. This is what we go through when we're solving these. Now, I told you that I was going to do something. I'm just going to do it on a whim to see if we can actually do it. It might be a little bit more cumbersome, but I'll show you just as a way to transition to the next video. But I'm going to do it after we finish off the idea. So I want to keep this cohesive. I'm going to show you how to do this a different way with an exponential after I do this one. So last example. Oh man, now I'm seeing logarithms everywhere. I'm seeing with the same base. I'm not seeing any constant term or a logarithm with a different base. I'm not seeing anything added over here that's a constant or subtracted. That's what we're looking for to determine the difference between common bases and having to use exponentials. So we don't have that. All right, so what are we going to do? Well, we got to combine all of these to get one logarithm on each side. Nothing added, subtracted, multiplied, any of that stuff. How we do it. Now, you have choices here. You can choose to distribute that 3 and get 3 log base 7 and 3 log base 7. And that 3 in both cases would move to an exponent and an exponent. That's true. Or you can combine these first. Either way is fine. Either way is appropriate. Because we have subtraction of 2 logarithms of the same base, we're going to create a quotient side of one logarithm. And that's going to be x over 2. We're also going to choose to move that exponent. Now I want you to notice what happens on the left-hand side. Now that we really don't need this anymore, and this is multiplication, this is going to move on as an exponent, but it's going to be an exponent on that entire argument. So it's going to go right there. And when we see that, I hope that you're understanding this. I hope you see it, that whether I distribute and then move it as an exponent, so x cubed and then 2 cubed, and then create a fraction, I get x cubed over 2 cubed. I'm going to get the same thing here. We know that exponents distribute across multiplication and division. Coefficients distribute across addition and subtraction. But because that subtraction becomes division in one logarithm, you're basically distributing over the same things. I said this a while back that as long as you're using an appropriate rule, you really can't get it wrong. Whether you distribute the 3 and then move it as an exponent and then create that fraction, or create the fraction, then move the exponent, and then distribute the 3. Either way, you're going to get the same exact result. It doesn't really matter. Just make sure you're following the rules and just don't make up your own math. That's the most common thing. So now this looks like what we want. We have 2 logarithms, the same base. We know that the only way this is equal is if our arguments or insides are equal. If we multiply both sides by 8, now we take a cube root of both sides. Remember, cube roots do not need plus and minus. The cube root of 128, you really need to simplify that. So we're thinking, what's the largest perfect cube that I have inside of there that's a factor of 128? That'd be 64. So 64 times 2. The cube root of 64 is 4. The cube root of 2 is, well, we really can't simplify that anymore. So we get 4 cube root of 2. That's a positive. If I plug it in here, that's positive. That's a constant. That's a constant. This is not creating any sort of a domain issue for us. It fits the bill for what we need here. That's our only valid solution. So I hope this made sense on the process of identifying, firstly, when you're going to be able to set your arguments equal. If you have all terms that are logarithms with the same base, combine it and set the insides equal. Now, I mentioned to you that in the next video, we're going to do some logarithms that require exponentials. I'm going to preface that right now with this example. So let's take a look at it under a slightly different lens. Now, could we use an exponential right here like I mentioned before? Yeah, you really could. You can make these both exponents on a base of 3. Base 3, log base 3, you've just composed a function on its inverse and simplify. Base 3, log base 3, function on its inverse, you simplify. Remember, what you do to one side, you have to do to the other. So if you have logarithms of the same base, you'd have the same base of an exponential. That's the only reason why this actually works. I hope that you're getting that. If you have different bases, you could not apply the same exponential to both sides of your equation. You have to have something else to do. It wouldn't work. That would be a big problem for us. So same base is why you're able to do both a 3 and a 3. You have to do the same thing to both sides of your equation. Now, here's a different lens. What if instead of just combining these as 2 logs on each side, we got all the logs on one side and we combine them to one logarithm and a constant on the other side? This is where the next video is going to go with it. And I want you to see it now to see that we get the same thing. So what if we did that? Well, because all of our terms are logarithms, if we got everything on one side, what would we have on the other side? Well, we'd have 0. That's okay. That is a constant. So I'm going to subtract these, we'll add that one, over to the other side. So we've subtracted and added. Now, hang on, all this stuff only works if we really combine to one logarithm on one side. Otherwise, we can't really use the process of changing to an exponential. We can't really set insides equal if we have more than one logarithm on one side, so we're still going to combine, which means we're still going to move our coefficients as exponents first. Taking the liberty of squaring the 5 and squaring the 10 to get 25 and 100 respectively so that I can omit one step, but check it out. All that stuff about combining was really important because when we combine, we should be able to do this all at one time. We should understand that all these logarithms are added or subtracted from one another. They all have the same base. You can create one logarithm, not a logarithm over a logarithm. That was change of base. One logarithm with a fraction inside. And I taught you my preferred technique. My preferred technique was not doing each little piece at a time. Just taking a look at the whole thing and saying all the positive logarithms and things being added are going to create factors on your numerator. All your negative logarithms or logarithms being subtracted will create factors on your denominator. Just make one fraction. So positive numerator minus denominator minus denominator plus numerator. Now, we can clean it up a little bit. And you really don't need to distribute this right now, but you will be doing it eventually. I probably shouldn't have done that. I always tell you don't distribute denominators. I even wrote a song about it. But I do want you to notice something. Please get this. This is going to be the exact process for the next video. When you see lots of logarithms and you have a constant that's not a logarithm, like if we would have had 7 there or something. We are going to gather all our logarithms on one side, the non-zero constant on the other. Now this happens to be a zero constant because we could have done it a different way. But if you don't have this way available to you, you just take that constant and put it over here on the right-hand side or left-hand side, whatever, one side. Get all your logarithms, combine them to 1. All your logarithms into 1. Get your constant on the right-hand side and then take a look at it. Can you write this as an exponential? Because if you can, an exponential is the inverse of a logarithm and it will solve this logarithm. Identify what your base is. Well, logarithms have separated the base from the exponent. The base is 3. The exponent is 0. So our base raised to the exponent will have to equal whatever our inside of our logarithm is. That's why we had to combine those, because you can't set base to exponent equal to all these different logarithms at once. It doesn't make sense. We need one logarithm to be able to do that. So base, exponent, and exponential, put those together and then sets it equal to the inside of your logarithm. That's what exponentials do. They are the inverse of some logarithm. So this is the way that we really deal with a logarithmic equation in general. Well, which way is easier? I don't know. This one doesn't require an exponential. This one's a pretty streamlined, but it only works sometimes, isn't it? Only if you have two logarithms, same base, one on each side. This one's going to work all the time, and especially when we have a non-zero constant. If you have a zero constant, understand that you really don't have a constant. You have all terms that are logarithms. So now we think through it. What's 3 to the 0 power? Well, I know that anything to the 0 power is 1. Oh, how do we get rid of denominators? We're going to multiply both sides. Our denominators simplify. This you can distribute. And we're seeing exactly the same math from right here. Same exact stuff. We're still going to get 1/3. So are there two ways to do it? Yes, but special cases typically make things a little bit easier. Why I wanted to give that to you was because in the next video, we're going to start basically right here. The idea that if you have a constant that is not in a logarithm, so a term that's not a logarithm, just some constant, we're going to gather our logarithms, constant on the side, combine, and then use an exponential. Because in general, it takes exponentials to solve logarithms. There's only a special case if you don't have that constant and you have the same base. I hope it makes sense. I'm going to see you for the next video when we start solving general logarithmic equations. Have a good day.